The last video in this playlist offers a more detailed description of the two non-boundary scan clusters that are present in our demonstration board. After watching this presentation, you will be able to explain how a non-boundary scan cluster can be tested using the surrounding boundary scan cells. Well, what we have here is again the block diagram of our demonstration board, and you should recall that the three boundary scan devices are the larger components that you see in the photograph of our board, and the two non-boundary scan clusters that are being addressed in this presentation are these two clusters that I have indicated now. The left cluster comprises two small integrated circuits, and then this other integrated circuit corresponds to this other cluster. It is of importance to point out that both clusters are strictly combinational, but there is one main difference between one case and the other, and the difference is that while this cluster is surrounded by cells that belong to the same boundary scan chain, this second cluster is surrounded by cells that belong to two different boundary scan chains. So this will be a slightly more complex case to consider than this one, because we have to deal only with one boundary scan chain in this case, but we will have to deal with two, synchronizing the actions between two boundary scan chains in the case of the second cluster. Well, since they are combinational clusters, as I have just indicated, basically what we will need to know is how many inputs and outputs have to be taken into consideration, and what are the boundary scan cells that are related to those inputs and outputs. So in the case of the first cluster, which is the one shown here, located within the first boundary scan chain, what we see is that we have 4 inputs and 8 outputs. Well, the number of inputs is actually more important, because it dictates the total number of test vectors that will have to be applied. If we wish to carry out an exhaustive testing, for example, then in this case we will need 2 to the power of 4, that is to say 16 test vectors. And in this case, because these test vectors are driven through the outputs that are controlled by this control signal of one of our octal buffers with boundary scan, then this cell will have to be taken into account as well. Otherwise, we might just tri-state these outputs and then no test vectors would be applied. So we will have to serialize 16 test vectors, and if we wish to carry out an exhaustive test, and for each of those test vectors, this cell will have to be loaded with a 0 to open or activate these outputs. The numbers indicated here represent the order of these cells in the corresponding boundary scan chains. So in the first device, since we have, if we go back here, the first device has 18 cells, which are represented here from 0 to 17. And then if we continue our notation, this will be cell number 18, 19, 20. And so that is why you see the outputs of the cluster being captured into boundary scan cells 20 to 27, and in both cases, as you already know, this belongs to boundary scan chain 0. So for each test vector, we will have to look at the logic pattern that has been captured into these 8-bit positions as they are shifted out. I leave it up to you to think about what other possible approaches might be considered for testing this cluster. What I mean is, would it be possible to test it using less than 16 test vectors and still guaranteeing 100% fault coverage? Or even if we still need to use 16 test vectors, is there a way to generate them that would be faster than just scanning them one by one, all 16 into this chain? Well, finally, the second cluster, which is the one indicated here, it comprises a larger number of inputs. So this is actually a more complex case, not only because it is located between two boundary scan chains. The inputs to the cluster are controlled through boundary scan cells belonging to chain number 0, while the outputs of the cluster are captured into cells belonging to boundary scan chain number 1, but also because we actually have 8 plus 2, we have 10 inputs to this cluster. So if we wish to carry out an exhaustive test, this will mean 1024 test vectors, and this will, of course, take longer. Now, we also have to take into account that actually, in this case, if we go back, you will see that this cluster is driven from pins that come, in most cases, they come from this second boundary scan IC, but these two control signals, they come from the first device, and this is what is represented here. So these cells belong to the leftmost device, while the second device, the one in the middle, is responsible for driving these test pins. Again, I ask you, is there a more practical way than just driving 1024 test vectors? Or even if we have to do so, could we make it faster in any way? These are questions that I leave up to you, and which we will consider again later when we talk about a more advanced test mode called pseudo-random test generation and parallel signature analysis.